For this video, we're going to be reading Chapter 7, Section 1 on weathering, and this can be found on page 153. In 1880, an impressive granite monument, Cleopatra's Needle, was moved from Egypt to Central Park in New York City. Although the monument had existed in Egypt far more than 3,500 years, in less than 75 years in New York City's climate, the monument had become dramatically worn and damaged. Today's markings on the surface can barely be read. Why do you think this happened? Changes occur every day to Earth's rocks and surface features. Just as the granite of Cleopatra's Needle has undergone changes, so too does granite in Earth's crust. The process by which rocks on or near Earth's surface break down and change is called weathering. The removal and transport of weathering material from one location to another is known as erosion. The process of weathering and erosion have been going on since the crust of Earth formed billions of years ago. Mechanical weathering. Before the agents of erosion can pick up and transport Earth materials, these materials must undergo some form of weathering. Weathering caused the results seen in Figure 7.1. Mechanical and chemical weathering are the two processes that can wear down rocks and minerals. Both types of weathering occur at the same time on Earth's landforms. The process by which rocks and minerals break down into smaller pieces is mechanical weathering, also called physical weathering. Mechanical weathering does not involve any change in a rock's composition, only changes in the size and sometimes the shape of the rock, as shown in Figure 7.2. A variety of factors are involved in mechanical weathering. Temperature. Temperature plays a significant role in mechanical weathering. When water freezes, it expands and increases in volume by approximately 9%. Thus, ice takes up approximately 9% more space than liquid water does. You have observed this increase in volume if you have ever made ice in an ice cube tray in a freezer. In many places on Earth's surface, water collects in the cracks of rocks and rock layers. If the temperature drops to the freezing point of the water, it freezes, expands, exerts pressure on the rocks, and may cause them to split, as shown in Figure 7.3a. When the temperature then increases, the ice in the cracks of rocks and rock layers. The repeated thawing and freezing of water in the cracks of rocks is called frost wedging. Frost wedging is also responsive for the formation of potholes in many roads in the northern United States in early spring, as shown in Figure 7.3b. Pressure. Pressure is another factor in mechanical weathering. Bedrock at great depths is under pressure from the overlying rock layers. When the overlying rock layers are removed, the pressure on the bedrock below is reduced. The bedrock surface, formerly buried, is then able to expand, and long curved cracks can form. These cracks, also known as joints, occur parallel to the surface of the rock. Reduction of pressure also allows existing cracks in the bedrock to widen. Over time, the outer layers of the rock are stripped away in succession, similar to an onion's layers being peeled off one by one. The process by which outer rock layers are stripped away is called exfoliation, shown in Figure 7.3c. Exfoliation often results in a dome-shaped formation such as Liberty Cap and Half Dome in Yosemite National Park and Stone Mountain in Georgia. Sometimes the effects of reduced pressure on rock layers are dramatic. For example, when several layers of overlying rocks are removed from a deep mine, the sudden decrease of pressure can cause large pieces of rock to explode off the walls of the mine tunnels. The roots of trees and other plants can wedge themselves into cracks in rocks. As the roots grow and expand, they can exert pressure on the rocks to split, as shown in Figure 7.3d. Chemical weathering. The process of which rocks and minerals undergo changes in their composition as the result of chemical reactions is called chemical weathering. Significant agents of chemical weathering include water, oxygen, carbon dioxide, and acids. Chemical reactions between rocks and water result in the formation of new minerals and the release of dissolved substances. The new minerals are different properties from those of the original rocks. For example, rust on an iron chain has a different chemical composition from one of the iron on which it formed. To some extent, the composition of rocks determines the effects that chemical weathering will have on them. Some minerals, such as calcite, may dissolve completely. Rocks and that contain calcite, such as limestone and marble, are also greatly affected by chemical weathering. Buildings and monuments made of these rocky readily show signs of wear resulting from weathering. Temperature is another significant factor in chemical weathering because it influences the rate at which chemical reactions occur. Usually, chemical reaction rates increase as temperatures increase. With all of these factors being equal, the rate of chemical weathering reactions doubles with each 10% Celsius increase in temperature. Water. Water is an important agent in chemical weathering because it can dissolve many kinds of minerals and rocks, as shown in Figure 7.4. Water has an active role in some reactions, while it simply serves as a medium through which other reactions occur. The reaction of water with other substances is known as hydrolysis. Hydrolysis occurs in the decomposition of silicate minerals, such as the decomposition of potassium feldspar into kaolinite, a fine-grained clay mineral common in soils. Oxygen. Like water, oxygen can combine with other substances. The chemical reaction of oxygen with other substances is called oxidation. Approximately 21% of Earth's atmosphere is oxygen gas. Iron in rocks and minerals readily combine with the atmospheric oxygen to form minerals that oxidize. A oxidized form of iron is shown in the following reaction. Common minerals that contain the reduced form of iron include magnetite, hornblende, biotite, and pyrite. Carbon dioxide. Another atmospheric gas that contributes to the chemical weathering process is carbon dioxide, which is produced by living organisms during the process of respiration. Yes. When carbon dioxide combines with water in the atmosphere, it forms a weak carbonic acid that falls to Earth's surface as precipitation. The formation of carbonic acid is shown in the figure in the following reaction. Carbonic acid reacts with minerals such as calcite in limestone and marble to dissolve rock. For example, limestone caverns, as shown in Figure 7.5, can form when carbonic acid dissolves in cellulite and limestone rocks. Carbonic acid can also affect silicate minerals such as mica and feldspar by reacting with elements in the minerals such as magnesium and calcium. This chemical weathering process results in the formation of clay minerals. High concentrations of carbonic acid accumulate in soil. When decaying organic matter and plant precipitation produce high levels of carbon dioxide, the water from the precipitation seeps into the ground and combines with carbon dioxide. Large amounts of carbonic acid become available for the process of chemical weathering. Acid precipitation. Another great agent of chemical weathering is acid precipitation, which is caused mainly by the oxidation of sulfur dioxide and nitrogen oxides that are released into the atmosphere by human activities. Sulfur dioxide forms from the industrial burning of fossil fuels, while nitrogen oxides are emitted from motor vehicle exhausts. These two gases combine with oxygen and water in the atmosphere to form sulfuric and nitric acids. We describe how acidic a solution is by using the pH scale. Figure 7.6 illustrates the pH scale. Lower the pH number, the greater the acidity of a substance. Acid precipitation is precipitation that has a pH value below 5.6. The pH of normal rainfall. Because acids can be harmful to many organisms and destructive to non-living things, acid precipitation creates problems. It adversely affects fish and aquatic plant pollutions in lakes. Most freshwater lakes have a natural pH in the range of 6 to 8. These lakes can support many kinds of amphibians, aquatic invertebrates, and fish. However, when the lake has become too acidic, the species diversity decreases as shown in Figure 7.1. The table indicates which organisms can survive at a particular pH. As you can see, wood frogs are able to survive at a lower pH than other species. What affects the rate of weathering? The natural weathering of Earth's materials occurs very slowly. For example, it may take 2,000 years to weather 1 centimeter of limestone, and yet most rocks weather at even slower rates. Certain conditions and interactions can accelerate or slow the weathering process as demonstrated in the GeoLab at the end of the chapter. Climate. The climate of the area is a major influence on the rate of chemical weathering of Earth's materials. Variables of climate include precipitation, temperature, and evaporation. The interaction between the temperature and precipitation has the greatest effect on a region's rate of weathering. Chemical weathering occurs readily in climates with warm temperatures, abundant rainfall, and less vegetation. These climate conditions produce thick soils that are rich in organic matter. When water from heavy rainfalls combine with the carbon dioxide and the organic matter to produce high levels of carbonic acid, the weathering process is accelerated. Chemical weathering is evident in tropical Central America, Southeast Asia, and other areas as shown in Figure 7.7. Conversely, physical weathering occurs readily in cool, dry climates. Physical weathering rates are highest in areas where water undergoes repeated freezing and thawing. Conditions in such climates do not favor chemical weathering because cool temperatures slow or inhibit chemical reactions. Little or no chemical weathering occurs in areas that are frigid year-round. The different rates of weathering caused by different climate conditions can be illustrated by a comparison of Asheville, North Carolina, and Phoenix, Arizona. Phoenix has dry, warm conditions. Temperatures do not drop from the freezing point of water, and humidity is low. In Asheville, temperatures sometimes drop below the freezing point during the colder months. Asheville has more monthly rainfall and higher levels of humidity than Phoenix does. As shown in Figure 7b, because of these differences in their climates, rocks and minerals in Asheville experience a higher rate of mechanical and chemical weathering than those in Phoenix do. Rock types and composition. A wide variety of rocks and minerals cover Earth's surface. The characteristics of rocks, including how hard or resistant they are to being broken down, depend on their type and composition. In general, sedimentary rocks are more easily weathered than harder indigenous rocks and metamorphic rocks. The dramatic landscape is the Bristol Bedlands of New Mexico, exhibits rock layers from different degrees of resistance to weathering, as illustrated in Figure 7.9. Surface area. Mechanical weathering breaks up rocks into smaller pieces. As the pieces get smaller, their surface areas increase, as illustrated in Figure 7.10. This means that the more total surface area is available for chemical weathering, thus the greater the total surface area. The more weathering that occurs, as you learned in the Discovery Lab. Topography and other variables. Earth's minerals cover the surface of slopes and level areas. Materials on level areas are likely to remain in place as they undergo changes. Thus, materials on slopes have a greater tendency to move as a result of gravity. As material moves down a slope, it exposes underlying rock and surfaces and thus provides more opportunities for weathering to occur. As you learned earlier, organisms also affect the rate of weathering. Decaying organic matter and living plant roots release carbon dioxide, which combines with water to produce acid, which in turn increases the weathering rate.